We've talked about operations on functions. We've talked about inverse functions. In order to fully be able to talk about inverse functions, we have to have an idea or understanding of a square root function. So a square root function is considered to be an inverse of a quadratic. But what happens is that the square root is oftentimes only the positive or the negative side of that quadratic. So what we're going to do today is go back and think about a quadratic and think about taking it and shifting it essentially 90 degrees. That square root will be a function that contains the square root of a variable. This is also known as a radical function. The domain of a square root function is not all reals because it is not a polynomial. So square roots are radicals. They are functions, but they are not polynomials. Remember, in order to be a polynomial, all of the exponents must be whole numbers. Square roots exponents are fractions. We can find the domain by setting whatever is under the radical greater than or equal to 0. So you find the domain of a square root by setting whatever is under the radical greater than or equal to 0. Similar to the translations and transformations of a quadratic, we have the translations and transformations of a square root. A square root function will be shifted in those same similar directions. It will be stretched in the same similar way. Okay. I can't remember if I have a pop-ups. The A value is going to make it wider or narrower. The H value is still going to move it left or right. It is still the opposite value. And the K is still going to be your up or down. A square root does not necessarily have a vertex, but it will have a starting point. And that starting point will still be at my HK. So what does the parent square root function look like? The parent square root function will have a domain x greater than or equal to 0. Because x is what's underneath the radical, and that is what needs range are going to be all the positive values that make that true. So the parent function range is y greater than or equal to 0. Just like if a quadratic is shifted up or down, it moves its range. The range is going to be dependent on the k value moving up or down in a square root function as well. It will also be affected by a, just like the quadratic was affected by a, because the a value could also reflect it. The domain and range of the square root are going to be the opposite of the x and y's of the parent quadratic. So if you think about the quadratic function, the x values were 0, 1, 2, 3. The y values were 0, 1, 4, 9. The square root is going to be the opposite. It's going to be 0, 1, 4, 9 here. 0, 1, 2, 3 there. And that should make sense because the square root of 1 is 1, square root of 4 is 2, square root of 9, 3. If you plug 9 in, you get 3. The square root will look like a quadratic translated 90 degrees to the right. It is the one side of a parabola. So again, if you like to trade your paper, do it as a parabola. Okay? Y equals the square root of x minus 3. Well, that negative 3 is going to shift the parent function to the right 3. That means your domain is x minus 3 greater than or equal to 0. But when we talk about the domain, we like to solve for x. So that means that its x value is greater than or equal to 3. The range is unaffected because I have no k value. So it remains y values greater than or equal to 3. And what we're going to do is we're going to take all the x values here and move them right 3 units. So my x table is just going to go right 3. So instead of 0, 3. Instead of 1, 4. Instead of 4, 7. Instead of 9, 12. My y's are unaffected because it was only h, which we know only affects x. So now we're at 3, 0, 4, 1, 7, 2, and off my page. So again, not a vertex, but it represents our starting point. So the negative 2 moves my graph right 2. The plus 5 is going to shift the parent function up 5 units. That right 2 and up 5 are going to affect my domain and range. My domain, again, comes from the idea that whatever is under the radical has to be positive. We know that the square root of a negative is imaginary. So we know that that x minus 2 must be positive, or else we can't plug in a number, which means that x is greater than or equal to 2 is my domain. My range is affected by A and K. Well, the A is still 1, but the K is 5. So that means that my Y values get shifted up 5. So Y will never be anything smaller than 5. So my table, again, is affected by that -2 and the +5. And then you plug your points. Again, taking into account that it's a parabola on its side. So now my graph is affected a little bit more. We have an A. The A is going to make my graph stretch in this case. So it's steeper. It's also negative, which means instead of my parent function looking like that, it gets reflected across the x-axis, and it's going to open upside down. So it is reflected. Stretch. Shifted down. One. And left 3. So going from the origin, where your parent function should start, we would shift it down 1 and left 3. And again, taking into account that it is reflected, instead of my next point normally going up 1, right 1, they would go down 1, left 1, but it's also stretched. So remember that A value affects the Y, not the X. So you would skip almost your 2 points on the X value in a way, so you could continue to maintain your perfect squares. So in this case, the 2 is going to move my x's at a different group. So we know we're starting a -3, -1. And if the plus h and times a came as 0, your alternative, so again I want to show you like a second table option, is to pick the numbers that would create perfect squares, right? So 0 makes negative 3 makes 0. The next perfect square is 1. So what x value could you pick to create a 1? The answer would be negative 2. Again, if we did the 0, 1, 4, 9, that x minus 3 would get you there. Negative 2 plus 3 is 1. The square root of 1 is 1. So that's where the 1 that you have here comes from. 1 times negative 2 is negative 2. Negative 2 minus 1 is negative 3. So you can see how instead of going down 1, right 1, you go down 2 because of my slope and right 1. So negative 2 is going to make it quicker. Again, my next x value of key point would be at 1. 4 minus 3 is 1. And again, plugging in that 1, 1 plus 3 is 4. Square root of 4 is 2. Negative 2 minus 1, negative 5. You could also get that by multiplying 0, 1, 2, 3 by negative 2 and subtracting your 1. Yeah. It was for y for quadratics too. Yeah. The a always affects the range, and the k always affects the range. The h is always going to move the x. If you had done the fourth point, it would have been at 6. And then your domain still comes from what's under the radical. Your range in this case gets flipped. So y's are usually greater than. The negative changes the inequality to less than, and then it's still your k. And then the last thing we had talked about with quadratics when graphing them was inequalities. The same thing will hold true with square root inequalities. Our solution set will still be similar, but again, it's that shading idea inside a region. So all of your transformations are still the same. The solid versus dash is still the same. So this inequality is less than, but not equal to. So your graph line would be dashed. The y values are below, but your range still has to come into play. So yes, they're below, but you can't shade below what the range would be for the normal inequality. So it's below. My domain is x minus 4 greater than or equal to 0 still. to 4. My starting point for my graph is going to be right 4 and down 6. So again, it's all of your x values being subtracted by or added by 4. So 0 plus 4 is 0, 1 plus 4 is 5, 4 plus 4 is 8, and 9 plus 4 would be 13. And then it's all your y values subtracted by 6. So negative 6, negative 7, negative 8, and negative, oh my goodness. They go up, not down, sorry. Negative 5, 4, and 3. This one's not reflected, sorry. So your graph is dashed. And again, below, so that's like inside, but it's cut off by this line here because that's part of the original range. So the original range says the y values have to be greater than or equal to negative 6, but the shading is dashed and below, so you're shading kind of inside here. And you can check that by picking a point within that. So solid above, reflected, so that flips your range, left 2, up 4. So you're starting at negative 2, positive 4, and again, your normal point would go up 1, right 1, so this is going to go right 1, down 1. It would go over 4 for the perfect square, and instead of up 2, down 2. Rushing through the points just because. Then it would technically go 9, which is like 7, and then 3. This one is solid. Y values are greater than, but again, restricted by the original range. So within here. Okay. You do not have to graph 19 or 20. So they're going to cross off 19 and 20. We didn't talk about anywhere like the x was being multiplied inside. So don't do 19 or 20. Otherwise, you should be okay.